All right, so our last class, we're right on schedule to finish up with our finite difference methods for initial value problems. And you'll see I'm trying some new software I learned about yesterday. Has a very strange name. It's called spelled MMHMM. It allows me to superimpose myself here. This is kind of fun. I can make myself disappear. I can change my size. So it's actually kind of fun. And if you watch closely, you'll see that your favorite professor gets decapitated periodically, particularly when I use this for my morning class, and particularly when I have my iPad in the view, it gets confused and it sometimes chops off my head. So you don't want to miss that. All right, so let's get rolling here. Oh, we got a chat already. Yes, the equation sheet. Yeah, and you emailed me about this, Giovanni. So I have to update the equation sheet. I will do that either tonight or tomorrow, and I'll let you know. I'll post the revised equation sheet on Blackboard, so you'll have that. I also need to send you, for those of you going to take it via Zoom, I also need to send you a new Zoom link for the exam on Wednesday, because it's obviously at a different time. So I'll do that as well. So the equation sheet, I'll get up. I'll let you know when it is up. And then I will also send a Zoom link. Great. Okay, so we've been talking about finite difference methods for IVPs, initial value problems. We've been focusing so far on single step methods for ordinary differential equations. And basically we have three methods: first order explicit, first order implicit, and Crank-Nicholson. And just remember the pros and cons in terms of accuracy and pros and cons in terms of numerical stability. So first order explicit and implicit are only first order accurate in time. The implicit aspect improves on stability, numerical stability. And then the Crank-Nicholson is both very stable numerically as well as very accurate, second order accurate specifically. So we're going to use those same three methods in a little bit for partial differential equations. So I'll show you how each of those three methods apply to PDEs as well. Oh yeah, I didn't do a fun little video for solutions to exam 2. Yes, I'll do that as well. Thanks for the reminder. Okay, so first, before I get to PDEs, I do want to discuss briefly some additional methods for ordinary differential equations. I'm not going to spend a lot of time on these, primarily because they do not extend to PDEs. So these are specifically for ordinary differential equations. They are used quite frequently for ODEs, but I'm not going to spend much time on them. I just want to give you kind of an overview. And here I've kind of summarized what I just said a moment ago about explicit methods and implicit methods. And just to remind us the pros and cons. So first order accurate, poor numerical stability properties. Implicit methods can be second order accurate, and they can have improved numerical stability properties. However, there's a however for both. In the case of explicit methods, the however is that even though they're easy to implement, and that's because they don't require the solution of the right-hand side, that f of tu at the current time step, only at the previous time step where we know it. And it is also easy to adapt for nonlinear differential equations. The however for implicit methods, everything sounds good here, that's great, but there is additional computational time per time step for implicit methods as compared to explicit methods. And if the equation is nonlinear, then that can create some extra difficulties for implicit methods. So there's pros and cons of each. And if we could be so bold as to put out a wish list and say, well, I'd like an IVP solver that has the best of both. I want to maintain the favorable accuracy and stability properties of implicit methods. That would be awesome. I'd also like to be able to capture the ease of implementation and easy adaptability for nonlinear equations of explicit methods. So if I could combine the best of both, then we'd really be golden. And that brings us to these two approaches to doing just that. So there are predictor corrector methods and multi-step methods. I've kind of alluded to multi-step methods already, in contrast to the single-step methods that we've been looking at. Predictor corrector methods have two steps. First, you would never guess, is to predict. So we're going to use an explicit method in order to predict the solution at the current time step. And then we're going to correct that solution. So there'll be a two-step process: predict the solution and then correct that solution. The correction step is going to use an implicit method at the current time step. So it's going to combine both explicit and implicit methods. And I'll show you a couple of examples of how we can do that. Multi-step methods are just what they sound like. So single-step methods, you just need the solution at the previous time step in order to get the solution at the current time step. For multi-step methods, we need the solution at multiple previous time steps in order to get the solution at the current time step. And in doing so, the hope would be that we can increase accuracy and or numerical stability. Again, I'm just going to give you a brief overview of these. They are very important, and a lot of textbooks will spend a lot of time on these. However, I don't want to spend too much time on these because they are specific to ODEs and they do not extend to PDEs. So predictor corrector, one very popular approach is Hume's method, and the predictor step and the corrector step are given here. So the predictor step is to use a first order explicit method. And so the right-hand side, you'll notice, is exactly what we had for the first order explicit method. It's UN plus delta t times f at tn un, where again, everything is approximated at the previous time step. And then the left-hand side, which is the solution at the current time step, we're just going to put a hat on it. So everything's the same, except we're going to put a hat simply to indicate that it's only the intermediate predicted solution. It's not the final solution at the current time step. So we get u hat at the current n plus first time step, and then we correct it. The correction is done using Crank-Nicholson. So we're going to use the u hat n plus 1, and then we're going to correct it to get the un plus 1. So we use the values at the previous time step in our first order explicit method to get a prediction for the solution at the new time level. And then we're going to take that and correct it to get un plus 1. All right, so it's Crank-Nicholson. So we have un plus delta t over 2 times f at tn un plus delta t over 2 f at tn plus 1 u hat n plus 1. Now, one thing you'll notice, last time in the Crank-Nicholson method, this term was actually on the left-hand side because it's n plus 1. So we don't know the solution yet, so we had to solve for it implicitly. Here, however, we do know the u hat n plus 1 because we got that in the prediction step. So even though we're using an implicit Crank-Nicholson method, we actually end up with an explicit expression for u at the current time step, un plus 1, because I know this value now, so I can evaluate f at the current time level using u hat n plus 1. Okay, so that's a key difference, and it simplifies things somewhat. So 2 steps: predict and then correct at each time step, and then you move forward. Increment forward in time, march forward in time, and you're good to go. Very straightforward. It's building on techniques that we already have in our toolbox. Another very popular approach is called the Runge-Kutta method, predictor corrector called Runge-Kutta. You may have heard of these. ODE 45 in MATLAB is based on Runge-Kutta methods, and they're very robust, very flexible, so you can have them, you can develop them at various levels of accuracy. And I'm not going to give you any equations at all. I'm just going to kind of walk through some points about Runge-Kutta. So it is a predictor corrector type method, and it has higher order accuracy. So we can basically decide whatever accuracy we want and then apply the appropriate Runge-Kutta method to get that level of accuracy. So the ODE 4.5 is actually using 4th and 5th order Runge-Kutta methods. And what's happening is the Runge-Kutta methods involve various function evaluations between time steps. So you have the previous time, you have the current time, you have f at tn, un, f at tn plus 1, un plus 1, and then you march forward. In Runge-Kutta, you take that time step and you divide it up into smaller little pieces. Might be 2 pieces, might be 3 pieces, 4 pieces, depending on the order of the method. So in a second order Runge-Kutta method, you divide each time step up into 2, so that you have 1 additional function evaluation halfway between the 2 time steps. As you increase the order, you need more and more of these function evaluations. They're typically still only conditionally stable, just like our explicit methods. However, they're not as unstable. In other words, the restrictions on the time step are typically much less restrictive than for explicit methods. So they're still unconditionally stable, but they're not nearly as bad in terms of the time step requirements as in first order explicit methods. This is probably one of the most widely used. As I said, it's built into MATLAB. There's Python functions that do basically the same thing. And the most popular version, again, you can pick whatever order you want. The most popular is the 4th order RK or Runge-Kutta method. And there are some examples in the Python tutorial that show how to do these. Okay, then multi-step methods. So that's predictor corrector. It's one approach to satisfying our IVP wish list. Multi-step methods are a second approach. So once again, instead of just having the previous solution at the previous time step, we're going to take advantage of the fact that we know the solution at multiple previous time steps. Now, that means we're going to have a starting method. So if I need the previous 2, then at the first time step, I only have 1 previous. I don't have 2 previous. So I'm going to have to use another method. So it might be a first order implicit or explicit method to get that first time step. And then I can start the multi-step method. If I need previous 2 or 3 or 4, then I'm going to have multiple methods to get me started before I've built up enough previous time step solutions in order to proceed. These come in the same 2 forms as our single step methods, explicit and implicit. Explicit methods are called Adams-Bashford and implicit Adams-Moulton. And again, there's multiple ones of each of these. Some books just kind of go on and on and on. They're like encyclopedias about all these different possible Adams-Bashford and Adams-Moulton methods. Again, I'm just going to give you some comments about these with no equations. So the 4th order Adams-Bashford method, just as an example, uses values of the right-hand side functions, so the f's, at the current and 3 previous time steps. So 4 total time steps in order to get a 4th order approximation. So whereas the 4th order Runge-Kutta method requires 3 new function evaluations, the 4th order Adams-Bashford method only requires 1 new function evaluation, and that's at the current time step. So the difference is, remember, Runge-Kutta is taking our time step and dividing it up into little pieces, whereas the multi-step method is using the same time steps that we already have. So I already have the solution at previous time levels. I don't have to recalculate them. I already have the function evaluations at them. I don't have to recalculate them. So the multi-step method takes advantage of that. The Adams-Bashford method specifically takes advantage of that. The Adams-Moulton, which results in implicit methods, They have better stability properties, as you would expect, because they're implicit, and they can be implemented in kind of a predictor corrector sort of framework, so that they kind of have this two-step aspect to them. So you could have an explicit predictor step using a Adams Bashford method. You could have an implicit corrector step using an Adams Moulton method. So this gets really complicated, really messy looking. It sometimes seems like we're just, when you look at these parts of the books, it seems like we're just coming up with every possible scenario and every possible algorithm, and it's not clear which one is the best in a given situation. So again, just to kind of put a final point on this, the Runge-Kutta methods are usually the most common. They're not perfect in terms of numerical stability, but they don't require previous time steps. So I can change the time step each time I do my Runge-Kutta if I want. So that gives me added flexibility. And so that's kind of the standard. But I just want you to be aware of these other methods as well. Once again, none of these can be extended to PDEs, which is why I'm not emphasizing them very much. Oh, Dilbert. Okay. Oh, this is a good one. So are you coming to the code mocking? The what? Code mocking is an engineering tradition. It happens whenever a software project is handed to a new engineer. The new engineer is required to mock the previous engineer's work in a public way. We spectators get to vote on whether the old code is killed or spared. I always love how his tie sticks up, kind of like the way mine looks when I wear a tie. Haha, his code is hilariously inefficient. Ouch, chest pain, kill it, kill it, kill it. Ah, the code is offending my engineering sensibilities. It's killing me. I forgot to mention that sometimes the code wins. So we've talked about this a little bit before. When the worst thing you can be asked to do in a coding context is your boss says, here's previous employee ABC, here's their code. It didn't work, but use this as a starting point and figure out why it didn't work and fix it. That's like the worst thing you can be asked to do, because you have to understand someone else's code, kind of have to get into their brain. No two codes look alike. No two coders code alike. And so you can be doing the same thing, but the way they've done it isn't the way you've done it. You got to figure it out. It's usually easier to write your own code, but there are times where you don't want to, because if it's a huge project, you want to be able to build on existing code whenever possible, particularly existing code that works. But anyway, this is kind of poking fun at the fact that looking at other people's code can be actually quite painful at times, entertaining sometimes, and painful other times. Every once in a while, someone will be super creative with their variable names. Most of us try to use variable names that are somewhat indicative of the actual quantity that we're trying to represent. Some people are like, maple tree. Maple tree equals whatever. And then everything is a tree. It's like, I don't know, maybe they lived on Maple Street growing up. I don't know. So anyway, it can be kind of fun. That's where people's personality comes out. All right, so for the rest of our time today, we're going to focus on PDEs and show how we can extend these single-step methods to PDEs. So let's kind of come back and review where we were with our ODEs. So for ODEs, the only independent variable is time. So our dependent variable U is just a function of time. So in a heat transfer context, that would be like if I have an object, just one object, it has a temperature, and I'm tracking that temperature with time. So it's just U as a function of T. As time changes, how does the one value of temperature evolve? In a PDE context, we now also have a spatial component. So we're still going to have the time evolution, but there's also going to be a spatial component of the evolution of the system. So in a heat transfer context, that would be like if I had maybe a bar, like my pencil. It has a temperature distribution along the length of the pencil, And then I want to see how does that evolve with time. So at every time step, I need to calculate all of the temperatures along the length of my pencil. So rather than just one value, it's now a whole bunch of values. So it's kind of like the time part of the ODEs and the spatial part of our boundary value problems that we discussed earlier in the previous chapter. So we're going to look at the 1D unsteady diffusion equation as a model of this. All of the methods that we develop for this can be extended to other more complicated situations as well. Okay, so let's start with just thinking about some properties. So these are initial value problems. So that means they're evolving in time, but there is also a spatial component. So let's say that x goes from 0 to L. And so that will be my spatial domain, and then we march forward in time. So in terms of our spatial grid, this is going to look like an ODE, as I just said. Sorry, like a boundary value problem. So I'll have I plus 1, and I minus 1. I starts with 1, 2, and then goes up to capital I plus 1 at the right boundary. So that's like boundary value problems. But now I also have time. So we start off at time is equal to 0, and we're marching forward in time. So 1, 2, and then generically we have a time step n, and then the next one is n plus 1, and we just keep progressing forward in time. Now, all of the, whenever I write down or draw the stencils, the finite difference stencils in the future, I'm just going to focus on this one little area. So you're going to see me do a lot of this. So this is just zoomed in. This is I plus 1, and I minus 1. And this is n, and this is n plus 1. And then we're going to look at how, where the x's are. The x marks the spots where those are. So we have an initial condition at t is equal to 0. We know the temperature, for example, all the way along the length of the bar for all x. And then we want to know how does that evolve with time. We're still going to think in terms of marching as we march in time. But now every time step, we have the whole x domain to solve for the solution in. So here's our 1D unsteady diffusion equation. So it's partial u, partial t plus alpha partial squared u partial x squared. Alpha here is a diffusivity. That's the rate at which whatever it is diffusing in the medium. U could be a temperature, in which case we're talking about heat conduction. U could be a U, in which case we're talking about momentum diffusion due to viscosity, like in fluid mechanics. U could be omega, like a vorticity diffusion in fluid mechanics. U could be a concentration or mass diffusion problem, where U is C, like in a chemical engineering context. So these equations, this equation in particular, pops up all over the place. And it's just something is being diffused, whether it's temperature or heat, whether it's momentum, whether it's concentration of something, it's being diffused is the idea. So we're going to go back and revisit each of our three methods: first order explicit, first order implicit, and Crank-Nicholson, but now applied to a PDE instead of an ODE. All right, so the first order explicit method. So the way explicit methods work for PDEs is that the spatial derivatives are all going to be evaluated at the previous time steps, and then we will use a forward difference for time. And that's going to give us an explicit expression. So it'll look something like this. Once again, this will be our stencil. So the X marks the spot is right here. It's at the nth time level. And let me get myself a little space here. So IN is where we are approximating the equation. So it's going to involve this point, and this point for the spatial derivative, and then this point and this point for the time derivative. That's a funny looking T. There we go. So if you block out the left and right, then it looks just like our first order explicit method before. All I've done is I've shifted it so now time is up instead of to the right. And we have the previous time level here, and then the next time level here. But now we have the X dependence as well, the spatial dependence. So that gives us the I plus 1, I minus 1. So let's just look at each term by itself. So we have partial U, partial T. So let's take a look at that. So we're going to use a forward difference. We're here, X marks the spot here. So we have to use a forward difference to pick up the value at the next time step. So partial U, partial T is UIN plus 1. That's this point right here. Minus UIN, that's this point right here. Divided by the distance between them, delta T. And just to remind us, that's order delta T. That's only first order accurate in time. Then on the right, we have alpha times the second derivative of U with respect to X. So that's going to look like this. We're going to use the second order accurate central difference in space, again, at the nth time level, because that's where the X is. X marks the spot. So partial squared U partial X squared is our usual second order accurate central difference approximation, UI plus 1n minus 2 UIN plus UI minus 1n over delta X squared. And that is second order accurate in space. So put them together. Here's partial U partial T. Here's the alpha partial squared U partial X squared. Then we do the usual thing where we put all the unknowns on the left and all the knowns on the right. The only unknown is the UI n plus 1. So that goes on the left. Everything else goes on the right because it's known. It's at the previous time step, the nth time step. So when you do that, when you solve for UIN plus 1, you get that's equal to UIN plus alpha delta T over delta X squared. Oh, Tesla finally landed their thingamajiggy, and it didn't explode this time. Woohoo! Yeah. Finger clapping, yes. It only took, what, 5-6 tries. Those guys know how to embrace risk and failure. Very different than the old NASA. All right. So I solve for the UIN plus 1. Now this alpha delta T over delta X squared, I'm going to call that S just to simplify things a bit. Here I have a UIN. So if I pull those two terms together here, then I have this as my right-hand side. Quantity 1 minus 2S times UIN plus S times the quantity UI plus 1N plus UI minus 1N. Again, all of this is at the previous time step. I know it already. So this is just UIN plus 1 is equal to this expression. I just march forward in time, march forward in time. The difference now is I also have the subscripts, UI plus 1, UI minus 1. So I now need to also sweep along the X direction. So these are all the interior points in X from 2 to capital I. I'm assuming I know the values of U at the boundaries, Dirichlet boundary conditions. And so I just need to sweep along the interior points. If I have some other boundary condition, just like in the boundary value problem case, then we can deal with that as well. But we'll just think Dirichlet for now to simplify our equations. All right. So basically the same idea, except in the ODE case, this was just applied at one point. And we literally went, what's U at the previous time level, and what's U at the next time level, UN plus 1. Evaluate one equation, we're done. Then we go ahead to the next time step, next time step. Here, we have to evaluate this equation, capital I minus 1 times, for each of the X points. So for each of the I's, 2, 3, 4, 5, up to capital I. So it's just more of the same. It's nothing new, just more of the same. A bunch of comments here. Notice we still have an explicit equation for UIN plus 1. Yeah, there's a whole bunch of i's now, but it's still an explicit expression for those values of UIN plus 1 based on what we know about the previous time step. So it's still an explicit method. As I just said, it does require us to sweep across our I values as we go to each time step. So it's capital I minus 1 as much work as for the ODE case. It is second order accurate in space and first order accurate in time based on the accuracy of the finite difference approximations that we used for the time and the space derivatives. We can vary the time step as we go from one time step to the next because it's a single step method still. So we don't need to worry about what was the solution at previous time steps, so we can change the time step as we go. So if, for example, we see that, oh boy, the solution's changing really rapidly in time, maybe I should take smaller time steps as I go, or it's not changing as rapidly in time, so maybe I can take bigger time steps and save some computational time. If you do the stability analysis, I'm not going to cover this. I'm not going to worry, you don't need to worry about this for PDEs, but just like we did numerical stability analysis for ODEs, we can do the same thing for the PDEs. It is more complicated, it is more involved, but you can do it. And you find that just like for the ODE case, it is conditionally stable. And the condition is that S has to be less than or equal to 1/2 in order for it to be stable. Now remember what S is. S is alpha delta T over delta X squared. So alpha is usually relatively small. That's a diffusivity, that's a property of the material. Delta T is usually small, and delta X squared is also small. Delta X is small, and you square it, it's even smaller. So you have to choose based on the physical alpha and your spatial discretization, your delta X, you need to choose your time step delta T accordingly so that we satisfy this very restrictive time step limitation for numerical stability. So once again, we're always concerned with two things. There's the accuracy. So I want an accurate time evolving solution. So that requires a certain time step. And I also, of course, need to make sure that it is a numerically stable solution. Usually, I can't say this with certainty for all problems, but in most cases, the restriction for stability is more restrictive than the necessarily small time steps for accuracy. That's not always the case, but usually the accuracy requirement on the time step is not as restrictive as the numerical stability restriction on the time step. All right, first order implicit method. Same reasons as before. We want to improve on the stability characteristics that we have for the explicit methods. So what we do is we move the X marks the spot once again. So for the explicit method, the X marks the spot was here. For the first order implicit method, the X marks the spot will be here. Again, just like for the ODE case. So now this is where we will approximate the equation. So in space, it's going to involve these 3 points now at the n plus first time level. And the time step is going to pick up using a backward difference, is going to pick up the solution at the previous time. So first order backward difference for time instead of first order forward difference in time. And central difference for the spatial derivatives at the n plus first time level instead of a central difference for the spatial derivatives at the nth time level. Okay, so again, just think, remember, X marks the spot is there. So now the time derivative looks like this. This is our first order accurate backward difference, UIN plus 1 minus UIN over delta T. Then we have our alpha times the second derivative, but now at the n plus first time level. So this is the same as before, I plus 1 minus 2 ui plus ui minus 1 over delta x squared. But instead of being at the nth time level, they're now at the n plus first time level. Now those three are all unknown. So all of these come to the left hand side. The only thing we do know is this term. So that's the only one that goes on the right. So now we have ui plus 1, ui minus 1 as unknowns at the n plus first time level. I've had the same S definition, alpha delta t over delta x squared. So now, rather than an explicit expression for ui n plus 1, we now have a tridiagonal system of equations to solve for all of these u's. Because again, I is all of the interior points in my domain. You okay? Doggy to the moon. I still don't know if it's doggy, doggy, or dodgy. Doge. Oh, see, I'm 0 for 3. It's Doge. Is it really?
Yeah.
Okay. All right. Well, I learned something today. I do know that it's worthless. Well, it will be. Yeah. Have you been following his SNL? So I think, is it this weekend? I think he's going to be on. So yeah, for the last 2 weeks, he's all excited. So he's been tweeting about various ideas for skits. And of course, everyone's mocking him, including the SNL people. They're like, why do I have to come to work on Saturday and put up with this guy? So there's a lot of people that aren't too happy about it. Interesting fella. All right. So we now have a tridiagonal problem to solve. That sounds familiar. It's exactly what we had for the boundary value problem. Now we're solving a tridiagonal problem at each time step. So as I'm marching forward in time, each time step, I do a tridiagonal solve using Thomas. I get the solution at the next time step. Then I take a step forward. I now have all these unknowns again. I do a tridiagonal solve, one tridiagonal solve, and then I'm done. So you guys are now working on the fin problem, right? The extended fin problem that we discussed a couple weeks ago. So this is like an extended fin problem at each time step that you have to solve. Bunch of comments. First order implicit method, it's first order accurate in time, second order accurate in space. So no improvement there. Same characteristics as the first order explicit method. We now have to solve a tridiagonal problem rather than just explicitly solve this equation at each point in X. It is strongly diagonally dominant, so it will give us a good accurate solution. So that's not a problem. And we do have an algorithm for doing it, the Thomas algorithm, which we know and love and works tremendously well. There are more computations per time step. So this is one thing I always have to keep in mind. So people say, oh, well, implicit methods are better than explicit methods. And in general, that's true. However, there are some competing factors. So whereas you can take bigger time steps because the numerical stability characteristics improve, so you're taking bigger time steps, but you're doing more computation per time step. So for example, if you can only double the time step as compared to an explicit method, but you have to do twice as much computation per time step, then it's going to take just as long to solve the problem on the computer. So the time step increase because of stability has to be sufficient to offset the fact that you're doing more calculation per time step. So there are trade-offs, and we can't just be like, well, implicit methods are always better than explicit methods. That's not necessarily true. However, I will say it is nice not to have to worry about choosing the time step for numerical stability. It's nice to be able to just focus purely on accuracy and not have to worry about stability. Okay, we still have the issue that we had with the ODEs, and that is we only have first order accuracy in time. So explicit, implicit, improve on stability, but we still have lousy accuracy in time. So we go to Crank-Nicholson, just like we did for the ODE case. So now the X marks the spot is going to be right here in the middle. Delta T over 2, delta T over 2. So it's now actually going to involve these 3 points and these 3 points. The reason is, for the time derivative, it's going to be these two, same two, but now it's a central difference. So it's a second order accurate central difference in time. But in order to get the spatial derivatives here, where we don't have any grid points, we have to approximate the second derivative here and here, and then take the average of those two to get it here, just like we did in the 1D ODE case. So this is what it looks like. Here is the second order accurate central difference in time, UIN plus 1 minus UIN over delta T. Then we have our alpha times the second derivative, but now we're going to average the second derivative at the n plus first time level and the second derivative at the previous nth time level. So then each of these get finite differenced using second order accurate central differences. So now I have the UI plus 1n plus 1 minus 2 UIN plus 1 plus UI minus 1n plus 1 over delta x squared. That's this term. And then I also have the UI plus 1n minus 2 UIN. Can I say it any faster? Plus UI minus 1n over delta x squared. That's this term. And then 1/2, I'm taking the average of those two estimates of the second derivative to give me the approximation at the mid time level. Now, when I pull all the unknowns to the left and all the knowns to the right, I get this expression. The first thing you'll notice is it looks more complicated on the right-hand side, right? So here I just had minus UIN on the right-hand side. Now I've got this whole mess on the right-hand side, but that's okay because I can calculate it. I know everything on the right-hand side, so it's not a problem. Just a little bit more calculation to get the D in my tridiagonal solve. On the left, it looks very similar. I have the UI plus 1, UI minus 1, just like before, just like the first order implicit method. Different coefficients, that's fine. That's my A, B, C, and then this is my D. Put that in the Thomas algorithm, and I solve it. So this is no more work than the first order implicit method, except that calculating the D does require a little bit more time. But other than that, this is very, very comparable to solving, because it's just a Thomas call for the implicit method. It's just very similar to the first order implicit method. Again, some comments. We get a tridiagonal system. It is diagonally dominant, so everything's fine with that. And again, just a little bit more work to get the right-hand side values. It is second order accurate in both space and time now, which makes it a very popular approach to solving initial value problems, because it's good with stability. It's second order accurate in both space and time, relatively easy to solve. It's just a Thomas call for each time step. So it's very straightforward. This is still unconditionally stable for all S. So what that means again is you don't have to worry about choosing your delta T for stability. You only have to worry about choosing it for accuracy, which you always have to do anyway. So that's perfectly fine. If you have Dirichlet boundary conditions at the boundaries, that's fine, no problem. If you have, say, Neumann or Robin boundary conditions, so there's derivatives, then you would evaluate those at the current time level. So that's no different than the boundary value problem stuff that we did in the previous chapter. One thing you'll notice, I haven't made a big deal about this, but if you look at these time derivative approximations for all three cases, they look exactly the same. I actually have to tell, this is why I keep emphasizing the X marks the spot, because you can't just look at the time derivative, how it's being finite differenced, and say, oh, well, that's clearly a forward difference. Oh, well, that's obviously a backward difference. Or, well, Obviously, that's a central difference. They all look exactly the same. All of them are this point minus this point divided by the distance between them. But in one case, because the X marks the spot is here, it's a forward difference. In one case, because the X marks the spot is here, it's a backward difference. In the third case, because the X marks the spot is here, it's a central difference. So just keep that in mind as you're studying. At some point, it'll probably be like 3 in the morning, and you're going to notice, what? These all look the same. Are my eyes just deceiving me? And you look and you look, nope, they all look the same. Castle said they're forward difference, backward difference, and central difference. How do I tell the difference between the differences? And you can't just by looking at them. Again, you need to know where the treasure lies, where the X marks the spot. Okay, so that's important. All right, let's do it. We'll finish up with a couple of examples and then we'll be done. So let's look at the 1D unsteady diffusion equation, the equation that we've been dealing with so far. The X domain will be from 0 to L. Let's say that the boundary conditions are 0 at both boundaries, and we have some initial distribution at t is equal to 0. So this would be like having a temperature. So my pencil, so I know the temperature at t is equal to 0 along the length of my pencil. And then as time progresses, I'm just calculating how the heat diffuses in my pencil. So 0, 0 on both ends. Start with f of x as the initial temperature distribution, and then track the temperature in time, u, as a function of x and t. So let's take a look at a case where alpha is 0.002. As I said, it's usually relatively small. The diffusivities are typically small numbers. We'll take the length to be 1, and then my initial condition is going to be this. These exponentials of something squared, those are Gaussian. A Gaussian looks like this. So it's the same as a normal distribution in statistics. So it's just a fun shape to work with. So this is t is equal to 0 right here. So this is the temperature distribution at t is equal to 0. And then as we go in time, you can see how the temperature distribution is kind of flattening out. That's what diffusion does. Diffusion always spreads the effect of the heat. So we start off with a concentrated heat distribution, temperature distribution, and then over time it diffuses out, diffuses out, diffuses out. And you're saying, wait, well, where does it go? Heat's conserved, right? Where does it go? Yeah, it diffuses out the ends. So even though the temperature is 0 at the two ends, I can have a gradient of temperature, and you can see that I do. There's a gradient of temperature, and that corresponds through Fourier's law to how much heat is actually leaving my pencil. Okay, so great. That's diffusion, 1D unsteady diffusion. Here's another situation, the 1D wave equation, where this actually looks quite similar. I have c squared instead of alpha. C is the speed of a wave in the material. But the main difference is, on the left-hand side, notice that it's a second-order derivative in time rather than a first-order derivative in time. This completely changes the character of the equation. So it's no longer a diffusion equation at all. In fact, there is no diffusion in this equation. It's a very different type of animal, even though the only fundamental difference is a second derivative instead of a first derivative. All right, so let's take a look at how these solutions behave. So where does this come from? Well, you know, the classic example is the vibration of elastic string. So this is for you stringed instrument guitar players. You know, as you pluck the string is vibrating at different frequencies, and it's creating different tones. So that's one very popular, common interpretation of the wave equation. Another one is if you had a longitudinal rod like this, and then you take a hammer and you bang on it. So you bang on it longitudinally, doink, and then you get waves traveling along back and forth the length of the rod. So the string is vibrating laterally, the rod is vibrating longitudinally. Either way, you get the same governing equation. So let's say that we'll just think in terms of a vibrating string, and we'll say that there's no displacement at the two ends, just like a stringed instrument. It's fastened down at the two ends. We'll have an initial displacement, f of x at t is equal to 0, and an initial velocity, g of x at t is equal to 0. We need two initial conditions because it's second order in time. The 1D unsteady diffusion equation was only first order in time, so we only need an initial condition for u. Now we need two initial conditions for u. So it'll be on the displacement. So that's the initial shape of the string at t is equal to 0. So like if you're plucking it, what's the shape just before you let go when you pluck it? And then you could also have an initial velocity. Now, if you pull it up and you just let go, then the initial velocity is 0. But it could be anything. I'm going to use a similar Gaussian distribution for the displacement. So I'm going to say that I'm going to pluck the string in the form of a Gaussian, which is kind of hard to do with your fingers, but just to have a nice smooth initial condition. And then my initial velocity is just going to be 0. So what I'm going to show you is I take the string, I give it a Gaussian distribution, sort of kind of like that, not quite. And then at t is equal to 0, I just let it go and let it vibrate back and forth and see what happens. So again, it's a similar initial condition to our 1D unsteady diffusion equation, but you'll see it has a very, very different behavior. So this is x and this is t. So here's our initial Gaussian distribution. Whoops, I missed it there. Here's our initial Gaussian distribution. Instead of seeing this diffuse out as the heat goes out the two ends, instead what you get is a wave. You get a right moving wave and an equivalent left moving wave. And the mathematics of that, I won't go through it, but the mathematics of that actually makes sense. So this difference in the form of the equation means that whatever goes to the right, you have to have something equivalent going to the left. So you have these two waves that are going equivalent waves, identical waves going to the left and to the right. And then they bounce off the wall. Because we have a zero displacement boundary condition at the two ends, the wave bounces off the wall and it's kind of like a swimmer. You know how a swimmer comes, when they're coming to the wall, they flip over. So it's kind of the same idea here. So here we have a positive wave. It hits the wall and it comes back as a negative wave. So we have a mountain that turns into an equivalent valley. It's of the same size, but it's now a valley going back. It will superimpose, the one from the left and right will superimpose here. You can't see underneath. And then they travel, and then they bounce off again. But now they bounce back as a positive wave. They superimpose when they cross and continue on their way to the left and right. And this goes on forever. There's no dissipation, there's no friction, there's no losses at all in the wave equation as it's been expressed here. So you just get these waves bouncing back and forth, superimposing positive and negative, and they just go on forever. Obviously, again, that's a very different behavior than the 1D unsteady diffusion equation, where the only difference is the time derivative is first order instead of second order. Okay, any questions about anything? Okay, so I will update the equation sheet. I'll put that on Blackboard. I'll let you know when that's been updated. I'll send you a new Zoom link. As with the previous two exams, the final exam will be in this same room, Bertaliata 104, if you're going to do it in person. If you have not done it in person before, but you wish to for the final, that's perfectly fine. But I just ask that you send me an email so I bring the right number of exams so that everybody has an exam. If you're going to do it via Zoom, that's fine. Again, I'll send the link out so that you have that. And that is on Wednesday. Exam is on Wednesday. You have 2 hours, plenty of time. It'll be less rushed than the other two exams. It will not be that much. It could be a little bit longer, but it's not going to be that much longer than the previous exams, even though you have 45 minutes more. It is cumulative. So as I told some students after class on Tuesday, basically the way I think about it is the more material you have stuffed in your brain that you need to be able to draw from for the exam, the more time I need to give you to do that. So on a regular exam with less material, I expect you to be able to sit down, read a problem, know what to do, and do it in a reasonable period of time. But for a cumulative exam, you may have to stop and think a little bit. Oh yeah, haven't done one of these for a while. How does that go? Try this, try that. But you should still have plenty of time. All right, everything else as far as format will be the same as the other two exams. Okay, that's it. Kind of sad, I know. We'll get through it together. If space is black, why is the sky blue? Oh my goodness. Now you bring that up? Yeah.